here are two homework problems. First of all, before even doing this, let's check what's going on with the fundamental theorem of linear maps. Well, dimension of V equals to dimension of null plus dimension of range. Since these two are the same, right? They have the same value. What's the dimension of V in this context? V is the domain of T, right? What's the dimension of V? What's the domain? 4, right? Okay. This is 4. If I say this is dimension is x, x plus x, so what's the dimension? 2. So whatever these are, null T and range T, they better be 2-dimensional. Okay. So think about 2-dimensional null space and 2-dimensional range. Okay. So, like, what's the simplest 2-dimensional thing you can think of in R4? Null T, we might as well have x comma y comma 0, 0, right? Right? That's 2-dimensional. That's like the simplest 2-dimensional you can think of, right? So can you think of something that would kill anything that's in here to 0? But then anything that's not here, if you have something in here, it could give you something here. What kind of map would do that? So think of this. You want T of x, y, z, w. This is the generic vector in R4. And I want it to be mapped to 0, 0. Because I need the range to be this way. So something, something. Okay? But at the same time, if these are zeros, I want these to be 0 as well. What kind of map could it be? Right? This definitely has this as the range, right? And anything that's in here, if you put it in this, you get 0, 0, 0, 0. So anything in here is also in the null. Is that okay? All right. Yeah, so of course you need to say something more, but this is almost, and I'm giving you everything. Now, of course, this is not the only answer. There's like infinitely many other answers. You could even switch W and Z. You could do W, Z, 0, 0. That's perfectly fine. Okay? Or you might think, rather than this, you want 0, 0, x, y. That could be another possibility. So you can have so many different variations of this. But whatever you do, you better have these two both to be dimension 2. Okay, now, what about this one? How would you prove this? That there cannot be something like this if 4 was switched to 5. What goes wrong if you change from 4 to 5?
Dimension B has to be 5.
Okay, so?
Not a natural number.
Yeah, it's not a natural number. So proof is the fundamental theorem of linear maps says that dimension of R5 is same as dimension of null of T plus dimension of range of T. And if these are the same, let's say this is K and that's K, right? And dimension of R5 is clearly 5. So you have 5 equals to 2K. K is 5 over 2, but dimension can only be integers, right? Natural numbers, so non-negative integers. So. But dimension can only be non-negative integers.